I'm otherwise going to pick up where we left off last time. Just to remind you, we're doing beam theory, and we got through developing most of the equations on the last lecture, but we didn't go through any examples. So today's lecture, we're going to go through a couple of examples, and particularly with respect to beam bending, and then subsequently with respect to developing the next set of equations that's looking at beams that have other unique geometric features that we can take a look at, particularly beams that are thin. One more reminder as we're getting started here, is there's still a number of you, a relatively small number by this point, but a number of you who are logging in with your own personal Gmail addresses rather than your WMISH email addresses. And just to remind you, if you are using your WMISH email address, you're going to be let into the meeting without asking permission. Otherwise, there's a possibility that I won't see the notification. And so there is a possibility that you won't get in. That's happened a couple of times. So make sure to use your WMISH email address to log in. Okay, so picking up where we left off last time, we had developed the beam theory equations, of which they are now shown here on the screen. The important concept here is that the equations are actually relatively simple. They have within them some of these features that we need to pay attention to. So first of all, we have the material. It shows up as a Young's modulus here in the equations. We have the geometry. Now that shows up a couple of places, IXX, IYY, and IXY. As I noted in last lecture, this IXY, two subscripts, is the very common way of representing that. In other textbooks, beyond my notes, you might most of the time, in fact, see this as IX and IY rather than having a double subscript there. I just like the symmetry of the double subscript, and so that's what I've done. Note also here that what we have is an equation. This is a differential equation, as you can see. Second derivative with respect to z of EI YY U comma ZZ plus EI XY V comma ZZ. Note U comma ZZ and V comma ZZ. These are again second derivatives. So this is a fourth order differential equation in the displacement field U and V. That is also often called the deflection of the beam, because that deflection is a measure of the reference axis displacement. So it's not wrong to call it a displacement, but because it is specifically with respect to one point within the cross-section, it's sometimes referred to as deflection instead. So it's a measure of the deflection of the entirety of the beam. And then last but not least, in this differential equation, we have on the right-hand side a distributed load term. We noted that if there was symmetry across the x or y axis, that IXY would be equal to 0, which simplifies the equations. And basically, what's really critical in that simplification when it exists is we're decoupling the two equations. There's no longer any term that shows up in both equations, and so the bending about one axis is entirely decoupled from the bending about the other axis. Note one more time that the overall equation that you're seeing here is a differential equation. It really applies along the reference line, so the derivatives are with respect to position along the reference line. And note also that this is at a point in the beam, so this is a cross-sectional differential equation, derivatives being with respect to the overall length of the beam, or I should say position within the length of the beam. Anyway, all of that being said, we also found that another way to express these same equations is in moment terms. So the applied moment at any point in the beam is now going to be equal to a generalized stiffness, in this case EIX or EIY, times a generalized displacement, in this case really the curvature of the beam. So that's what we came up with last time. So now I think it's worth going through. We're going to go through and do what I would call a relatively simple example. And then we'll do a second example, which is somewhat more complex, although ultimately not very difficult either. We're going to do the first one entirely using variable, it's going to be theoretically derived, and then we'll actually put some numbers into the second example. So here's a cantilever beam. The way I've drawn this, the left edge over here is fixed, so there's no displacement or deflection of the beam at the left edge. We don't know what the deflection of the beam at the right edge is yet. Of course, that's one of the things that we're going to solve for. We'll also have another boundary condition that's going to show up at the left. We'll have a couple of boundary conditions that show up at the right. There'll actually be several ways to express the boundary conditions. Now, recall these equations are just simply the equations that we saw on the last slide, so there's nothing new in those equations. Now we're just going to apply them. Now, when you are on an exam or a homework, if you're looking at the beam and it's similar to what I've drawn here, unless explicitly stated what the cross-sectional area looks like of the beam, you can sort of begin to make some assumptions, and in many cases, those assumptions are perfectly reasonable unless you're explicitly told something else must be done. So, for example, this is a two-dimensional problem. I don't give you the cross-section. We're going to assume that what I've given you is the actual IX, IY, and IXY values. And so as givens, you don't have to compute them. That makes life a little bit easier. Unless you're told otherwise, if you have a two-dimensional problem like this, slightly tangentially, this is actually a one-dimensional problem when it comes right down to it, because in the plane of the deflection of this problem, of this 2D problem, there's really only one deflection to track. So what we're going to find is that that makes it even simpler. Anyway, bottom line statement from this is that unless you're told otherwise, it's perhaps reasonable to assume that there is symmetry in the cross section. So we could go ahead and say that that value is equal to 0. We can say that, oops, I made a mistake in my drawing here. We're going to say this value is equal to 0. And last but not least, we're going to say that the out of plane deflection is going to be equal to 0. So if we look at the way these coordinates are set up, looks like we've got the z along the long axis and we've got x in plane. So deflections in the y direction are going to be assumed to be 0. So ultimately, we can essentially cross out v terms. So this one here also would go to 0. So that's some important takeaways. Last but not least, of course, we need to identify what loads are being applied. As you're looking at this beam, you can see that we're applying a constant distributed load, and we're going to say that distributed load is in the x direction. So there is no distributed load in the y direction unless you're told otherwise, and so we can draw an arrow through that. And so ultimately what you've seen is we've basically crossed out the entirety of the second equation, and all we have left is the first equation for these simple two-dimensional, which are actually one-dimensional problems. So here I'm just essentially simplifying it as I described previously. Again, this one goes to 0. This one will go to 0 because that's got the v comma zz term in it. And so this is now the governing differential equation, the top one of the two differential equations. The bottom one is now a moment curvature relationship. Again, curvature, second derivative of the displacement field. So this is the same equations, just slightly more compactly defined. Now, we're going to skip. Here's how we go ahead and solve this problem. I'll make note of an additional item. In fact, let me go back one slide. Here is the equation. I'm going to put a big box around it. This is really the governing differential equation. This other equation, the one down here, can actually be directly computed from this boxed equation. So the boxed equation is the really important one. Now, as I mentioned, it's important to recognize that this equation is it's the differential equation that governs the deflection of a cross section, and this is in the field going from the left side of the beam to the right side of the beam. But again, unless you're told otherwise, you can start to make some additional assumptions that even make this somewhat easier. So that is, unless you're told otherwise, it's reasonable to assume that the Young's modulus is constant over the beam. And unless you're told otherwise, or alternatively, if the image indicates otherwise, it's reasonable to assume that the area moment of inertia is also going to be constant over the entirety of the beam. Again, if we look at this image that's on the screen, there's nothing here to suggest that that assumption is not true. And so it's reasonable for you to state that as assumption. So this top equation now becomes the second derivative of a constant term times a second derivative. Well, what do you do? When these are constant, you can pull them outside. The derivative then can go and be applied directly to u comma zz. So you're taking two more derivatives of u comma zz with respect to zz, and the net result of that is the top equation shown here. So for a constant cross section with constant material properties in the beam, in this two-dimensional problem with one-dimensional deflection, the beam theory equations simplify to being just this fourth-order differential equation, with the right-hand side, P of x, being the distributed load. Okay, again, looking at the diagram, I may, at some point in the future, give you a distributed load that's not constant, but according to the diagram, it's reasonable to say, well, hey, that looks a lot like a constant load, so now the right-hand side is a constant. So how do we solve this differential equation? Well, you know, life's pretty easy in this case, obviously set up to be a very easy first demonstration of beam theory. But to solve these equations, we have a fourth-order differential equation, fourth-order derivative equal to a constant. We simply then integrate. So the second equation shown here on the list, EI u comma z, third derivative is now going to be equal to px times z. So we're integrating with respect to z. And we can't forget to add the integration constant, this time called C1. Okay, life, again, still pretty easy. We can integrate a second time. EI u comma zz is equal to px z squared over 2 plus c1z plus c2. Again, that's very simple integration. You guys have that, no problem. What's notable here about this equation, and let me just make a little note here. I'm going to say that this equation has actually shown up for us previously. Let me go back a slide. And that is this equation. That is my. So the moments about y are equal to ei yy u comma zz. So this equation here is nothing more than my. Now I saw Nicole had asked a question in the chat window. Let me open the chat window up and read that real quickly. For some reason, it's not showing up on my screen. Oh, there it is. How do you know the distributed load Px is Px and not Py? So again, by our coordinate system that we set up, we set x as positive upwards here in the diagram, z along the axis. The load, distributed load, is applied in the x direction, and so it's Px rather than Py. David asks, why not minus Py? Well, that gets into sort of the semantics of how you happen to be choosing what your distributed load is. So if I were to actually further describe what Px is, I could say it's equal to, say, minus rho Ag, and the minus sign would come in there, but it would remain positive here. So David, I think that answers your question. What I would suggest as a general rule is that the equation as written and boxed here is the definition of the equation. I would solve the equation as written, and then ultimately when you plug in the known distributed load, track your sign in the known distributed load. Okay, so we have had, now we've integrated twice, we got to the moment equation, and now we know the moment is actually a quadratic equation. So the moment in this problem is going to be equal to px z squared over 2 plus c1z plus c2. Now we got to be a little bit careful about that because we don't know what c1 and c2 are yet, so we'll return to that at some point. Note also, just somewhat tangentially, but this equation here is going to be the resultant on the face. So if we had happened to take a free body diagram, something that looked like this, where I've made a cut maybe here, the shear resultant on that face is going to be this third derivative equation. So the fourth derivative equation is the distributed load. The third derivative equation is the resultant force. The second derivative equation happens to work out to be the moment, but that is something we'll encounter again later. So it's just a slight tangent to what we have been talking about so far. Anyway, bottom line, what do? Well, we continue integrating. We integrate one more time. We get px z cubed over 6 plus c1z squared over 2 plus c2z plus c3. Last but not least, we integrate one more time, and we get that the deflection u, in this case we're multiplying by EI. In all of these we're multiplying by EI on the left-hand side just to keep the right-hand side cleaner. Anyway, so EI u of z, this is now u as a function of z. It's no longer a derivative. This is the deflection of the beam in the x direction is going to be equal to px z to the fourth over 24 plus c1z cubed over 6 plus c2z squared over 2 plus c3z plus c4. So ultimately, what do we find? We find that there are 4 integration constants that arrive out of the 4 integrations that we did. We found that there is a distributed load equation, there's a shear resultant equation, there's a moment equation. By the way, this third equation down now is the EI value times, we'll say theta, where theta is slope. Okay, so this is a slope equation multiplied by EI, and then last, of course, is the deflection of the midline of the beam. So if you're solving these problems, recognize that each of these equations is meaningful. Okay, they're not just steps along the process. Okay, I'm not seeing any other questions at the moment, so we'll go ahead and move forward. The next step, of course, is to, well, you guys tell me, what would the next step be?
Find the boundary conditions.
Yeah, so we need to find these integration constants. Of course, the only way to find integration constants, at least as it applies to this problem, is to identify boundary conditions that help us solve for them. So I'm not sure who mentioned that, but whoever it was, why don't you throw one out for me? Please give me a boundary condition.
You could say the slope or deflection at the origin is 0.
Excellent. I see that was Nicholas. Thank you, Nicholas, for stating that. I would say that's a really good observation, so we'll use that first. Okay, again, we're looking at the left-hand side, the slope, u at the position z equals 0. That's where we are here. Of course, this is a midline, so we're looking at the deflection of the midline here. That is going to be equal to 0. Lo and behold, that means that this fourth equation, we're just plugging in z equals 0. So this is 0, 0, 0, 0, and C4. So C4 has to be equal to 0. Boom, no problem. The next thing, of course, that we can do is we look at the slope. Now, the slope at this point, this is the slope of the midline. Now, what's useful here, I think, is for people to begin to interpret what the result of this is likely to be. You have to use good judgment as you're solving these problems. And if I were to draw a line on, a line deflection, so here's my beam. I'm going to say the left-hand side is fixed. That is the straight line that represents the undeformed beam. If one had to intuitively draw what the deflection is going to be, well, what do we know? We know it's going to be something like this. Okay, and what we're seeing here is at the root, at this location here, the slope is 0 intuitively, and that's the boundary condition that we're using. The slope, also in my notational scheme here, we're going to call it u prime, so it's the first derivative. On the prior slide, we said that that also could be called theta, but lo and behold, that's going to be equal to 0. So, looking at this equation, so slope 0 here, we put that on the left-hand side of this equation. And z is equal to 0, so 0, 0, 0, C3 is therefore going to be equal to 0. So we've knocked out 2 out of the 4 integration constants. Let's look at the next set. Now we can actually choose, before I do that, anybody else want to throw out some additional potential boundary conditions that we could evaluate?
Would the shear at L be 0?
Okay, so that's a great question, and the answer is yes. However, we have to be a little bit careful. Okay, let me draw on the blackboard instead of on the slides here. So keep in mind what is it that we're solving? By the way, who asked that question? Just so that I can know.
That was me, Alex Hines.
Alex. Okay, thanks, Alex. Oh, shoot, I don't see your face, but thanks for the question. So keep in mind what these are. These are differential equations that govern the beam deflection within the beam. Okay, within the beam is an important statement there. So what you've described is a boundary condition. It's the shear on the right-hand side. So if we wanted to examine that, that would be a great thing to examine. We could take a free body diagram. So if this is the entirety of the beam, okay, we could draw a free body diagram essentially by taking a cut there. Okay, and the question then becomes, well, what is the resultant force on this face? That's V at that point, the shear resultant at this point. And what you, of course, recognize is that there's still going to be some distributed load over this small distance between where you took the cut and the edge. Okay, we'll call that dz. And in this domain, of course, if we sum the force, well, that was a terrible sum sign here. Let me try again. Sum the forces in the y direction, they're going to be equal to 0. Well, V will only be 0 in the limit as dz goes to 0. Okay, and of course we recognize that, yeah, we're going to drive that all the way up to the edge. And so at this point, if we were to complete this argument, so I could say plus V this is at L, so V at L. Now, even though I've drawn the arrows downwards, the overall force would be equal to plus px, because remember, the direction we're going to assume was positive. Even though I drew it negative, we're going to track the negative sign in the value of px. So dz is equal to 0. And then in the limit of this equation, dz goes to 0. Then we're going to find that V of L is equal to 0. So absolutely right, Alex. Good observation. I'll leave this on the board here for just a second if people are trying to capture that. But it turns out I didn't choose that one in this particular problem. Why didn't I choose it? Well, let me go back now. I hope you guys have had time to capture that if you wanted. If not, I can come back to that later. If I go back to these equations, we could actually then apply Px z equal to L plus C1 is equal to 0. And that would give us sort of C1 implicitly. So that would be the third equation. However, I truncated at the second equation and I chose a different boundary condition. So Alex, your statement would be a perfectly acceptable way to do the problem, but it's not the way that I did it here. Okay, so any other ones that we would like to throw out? Let me give you guys a hint too as you're doing these problems. This idea of thinking of these equations as meaningful to you gives you hints at where your boundary conditions can come in. So we called this one the shear equation. This was shear. That's the V equation. We said it was the moment equation. And this is the slope equation. And then this is the deflection equation. So shear, moment, slope, and deflection are where we can apply the boundary conditions. We did a deflection one. We did a slope one. Actually, I'm going to pull two moment equations as my remaining boundary conditions. So that's what, it's probably flashed on your screen a couple of times already. The first one is really the one that's written last. That's the moment at the end. Okay, so the moment at L, I chose to be equal to 0 by observation. And that, again, would take us back to this idea of the, that we went through on the blackboard. I took this free body diagram cut, and here's my resultant V. Here's my, the distributed load in the limit as dz goes to 0. If we're taking moments on the right-hand side, what do we get? Well, relative to that, we would say it's the distributed load times dz over 2 is the moment arm. So the distributed load sort of at the midpoint of dz times, of course, because the unit on distributed load is equal to force per unit length, so we need to multiply it by dz again. So we get a dz times rho x. Sorry, let me make that a little bit more clear. So this is rho x, or little px, I guess, times dz over 2. Now, if we're doing, we'll say moments counterclockwise positive, so that would be about the end point. That would be a positive number plus the moment at L is equal to 0. And by the same arguments, and in fact faster this time, because we get a dz squared over 2, the limit of that equation as dz goes to 0 as we approach the edge means that m at L is equal to 0. Okay, so that's the logic that we apply when we say that the moment at the end is equal to 0. Okay, and another argument that can be made is we can look at the moment at the left edge. That's the moment at 0. Nicole, I saw your question. Let me get back to it at the beginning or in a minute. But the moment at the left edge, how do we apply the moment at the left edge? Well, we recognize that for the purpose of computing the moment over here at this edge, we can replace the distributed load with a single force that it's statically equivalent load. So I can apply some force here that's equal to the entire distributed load times the length, because that's the total force, so Px times L, and the moment arm of that is going to be L over 2, so I'll say L over 2. And so here, that shows up right here. So the moment at the left edge is the total resultant force px times L times the moment arm L over 2. And so the combination of these two moments that we've now computed gives us these last constants, C1 and C2. Note there's another boundary condition. Basically what Alex had suggested doing at the right-hand side, we could do something similar at the left-hand side, and that would be to take a cut at the left-hand side and draw our resultant force here, V of 0. And of course, that's going to be offset by the distributed load along the entire length. We could do the sum of the forces in Y again. And so another reasonable boundary condition could have been V at L, or I'm sorry, V at 0. And we would have a viable boundary condition there. Again, in this particular problem, there are a number of different ways we could approach it. So Ethan's point, the moment at the wall must be equal to the moment generated by the distributed load. So that is absolutely true, Ethan. That is, obviously I've stated it already. This one here, M0, you stated it, I think, before I did. So thank you. Nicole asks, why do you take the limit as dz goes to 0? Anytime I'm taking the limit, in order to apply the sum of the forces there, if I took this boundary condition cut, I'm examining as we get closer and closer to the boundary. So the boundary exists when dx is equal to, or I'm sorry, dz is equal to 0. That's when you're actually at the boundary rather than somewhere inside the beam. So I hope that answers that question. Okay, so bottom line, here we have solved for all four constants. C3 and C4 are 0. C1 and C2 can be expressed that way. And so here is our answer. We just plug and chug those constants into the equation. We see that this is an equation. It's a fourth order equation. So the overall deflection as a function of z goes as the power 4 minus the power 3 plus the power 2 of z. And, we could do things like sanity check. Anybody have a suggested sanity check for me? Nobody wants to suggest a sanity check? So Tyler suggests the maximum deflection should occur at L. That's a great sanity check. And if we plugged in that number, in order to determine if it was the maximum, probably the best way to do it would be to plot this equation. And we would determine ultimately that that is correct. Ethan suggests make sure the deflection is 0 at the origin. That's another great sanity check. Thanks, Ethan. Absolutely. And this one by inspection, we plug in z equals 0 and we find the deflection is 0. Another thing that we could do is we can go back one more slide. We can also do a sanity check. Now that we know C1, C2, and C3, we could equivalently check the slope is equal to 0 at the origin, and that's by looking at C3. Now that was also a boundary condition that we use, so that's not a terribly useful one in this example, but conceptually is something else that we could do. Okay, any questions on that simple example before we move on to this other one? Okay, not hearing any questions, I'll go ahead and move on. Now, I've decided, on this slide it said this example is likely not going to be given in lecture. I decided to give it to you this year because I feel like we're okay on time and it's worth going through a second example because these beam theory calculations are actually pretty important to our understanding of structural mechanics. They show up very frequently in in aircraft structures and spacecraft structures. So we'll go ahead and do this example. So here's another problem. Now it's really a two-dimensional problem. I've got deflections both in the X and Y direction. The Z direction is still the direction aligned with the axis of the beam, so the length of the beam along in the Z direction. Now I'm going to use some numbers here for the sake of argument. I'll say that the overall length of this thing is 100. I apparently failed to put the units on here, so the unit on that length would be inches. In this case, the modulus would be mega psi, 30 mega psi for the modulus, and the force is 100 newtons. And what I'm asking you for with this problem, where really what's going on, the force, so here I'm actually saying F is equal to 1,000, but I'm applying it 2 times at the end in the Y direction and 1 time along the axis of the beam direction. So, that's something we can keep track of as well. In the end, what am I asking you for? I'm asking you for the overall resultant force. I want to know the shear resultant in the X direction as a function of Z. I want to know My, Mx, and Mz, all 3 of those. And then I'd like to also know strain and stress in the beam. By the way, before we move too much past it, I'll just remind you that once we know the deflection in this problem that we just did, we can compute strain and stress really quite easily because we had strain and stress equations. They were used to develop these moment equations that you see here on the board, and so you can calculate the strain and stress very easily from the deflection field. Okay, so anyway, what do we do? Well, the first thing to do in any problem like this is to sit down and make mention of what precisely you know. So one of the things that we know is the moment about the Z-axis. Okay, the moment about the Z-axis is going to be the force, 2F, times the distance from the reference point, that is the centroid of this beam, which for the problem that we have here with a 3-inch by 6-inch cross-section would be 3/2, so 3 halves. And so in this problem, we have a moment about Z-axis, 3,000 inch-pounds. I'm going to go through this fairly quickly just for the sake of, I wanted to show it to you, but I'm going to nevertheless go through it fairly quickly. So, slow me down if you need to. This is available in the course pack if you'd like to make reference to that. So one of the boundary conditions we could compute would be to compute the moments at Z equal L due to F about its centroid. So we can compute the entirety of the moment, and we can now recognize that that moment has components that are given here. That is that we have a moment arm that is 3 times the J direction plus 1.5 times the I direction crossed with the F vector, which is now in the K direction. So I and J can be crossed with K. You have to be attentive to the signs. So I cross K is equal to minus J, and J cross K is equal to positive I. And so what we get out of that cross product is 3F in the I direction minus 1.5F in the J direction. So why do I show you this? Part of the reason why I'm showing you this example is just to recognize that moments, even though often we drop the vector representation of them just for convenience, especially if it's obvious, moments themselves are vectors, just like forces are vectors, and so they can be written with components. So there you go, our moment components at this point, moments about the x-axis and moments about the y-axis at the end, Z equals L, minus 3,000, plus 3,000 and minus 1,500 inch-pounds. So summarizing everything we know about this problem, we know that the axial load, because that was what was applied, is 1,000 pounds. We know the shear forces Sx is equal to 0. Sy is equal to 2,000 pounds. We know the moments at the end, Mx 3,000, My 1,500 in the negative direction, Mz 3,000, and the distributed load is 0. I've just realized, and I want to draw your attention to it just to alleviate any confusion. Here I'm using Sx and Sy to represent shear in the X and Y directions. Those are shear resultants. I believe that's the way I defined them at the beginning of our lectures on beam theory. And when we were going through the simplistic example, I think I called that V, shear. So just make note of the fact that I've used both of those. Probably I should go back and make sure that everybody's aware that we're calling that shear. And if we want to be consistent, maybe call it S. The reason I called it V is because in other textbooks, some textbooks use S, some textbooks use V. As my mind switches back to the days of my youth to the days of my maturity, I've experienced both. And so sometimes I try and pretend I'm younger than I am and go back to the old ways. Anyway, so what do we know? Well, we go back to these beam theory calculations and the beam equations that we derived last lecture and reviewed at the beginning of this lecture. One of those equations was that the change in the shear force in the x direction as a function of z is equal to minus the distributed load. We happen to know that the distributed load in the problem is 0, so we integrate 0 and we ultimately get a constant. And for the x direction, now in order to see the x direction, we need to go back to the diagram. The x direction would be something in this direction. We don't have any forces in that direction. We have some in the y. So get rid of that. We're going to call that one 0. It's a constant. We know it's a constant 0. Similarly, dsy dz is equal to minus py. Again, py is equal to 0. There's no distributed load, so integrate once. We get that sy is equal to a constant. We already solved that number. We know at the right edge, or at the position z is equal to L, it was 2,000. And if it's a constant, it remains a constant 2,000. Last but not least, of course, dp dz. So this is the change in the axial load as a function of position within the beam is equal to minus pz, little pz, so the distributed axial load. That, of course, was going to be equal to 0 as well. So the p value is constant and known. So because there are no distributed axial loads or torques, we're going to know that p is constant in 1,000 pounds, and the moment about the z-axis is 3,000 pounds. So the moment about z is the long axis of the beam, measured about the centroid. All right, I don't want to move too quickly. Am I leaving you behind? If so, please pop a question in the chat window or turn your mic on and ask a question. Okay, now keep in mind another equation that we derived was this one, that is dmx dz is equal to the shear force. We now know the shear force is a constant, 2,000, so we can integrate and get moment. So mx is 2,000 z plus the constant. We can apply the boundary condition at the end where z was 100 inches. And therefore, knowing that value is 3,000, we can say that c is equal to minus 197,000. And so now from that, we have a moment equation about the z-axis, no problem, pretty easy. Do the same thing for my. The only difference here is this equation has the minus sign in it. We saw and talked about that extensively last time. So again, this is going to be equal to 0. The shear force in the x direction is 0, so we can say that the moment is now going to be equal to a constant. We can apply the boundary condition that we saw at the end of the beam where my was equal to minus 1,500 inch-pounds. And so we know this is going to be a constant within the entirety of the beam. So Nicole asks for the slide that says summarizing at the end. I'm confused where some of those numbers came from. So Nicole, they came from the very beginning of the definition of this problem. Let's see here. So basically what we're pulling from is here, where the force is equal to 1,000 pounds. That plus the diagram where we have 2F and F, two forces really, where they're scaled by this magnitude F equal to 1,000. And then from that, we computed then the moments at the end. That's what these other slides were. And then we subsequently use those as boundary conditions in these slides. Okay, so bottom line, we're doing pretty well here. We've been able to express the moment as a function of position in the beam, the axial load as a function of position in the beam, the shear load as a function of position in the beam. All of those are resultant values that we've been able to compute from what was given. Last but not least, we need to find the stress and strain. This is the equation, again, an equation that we derived last time. We can say that the bending stress is composed of only really 3 parts. Well, I should say the total stress is only 3 parts. One is the stretch of the reference axis, or the strain of the reference axis, times A, minus x u comma zz minus y comma vzz. So these are curvatures. And ultimately, what do we recognize? Well, we recognize that stress is equal to E times A times epsilon, right? So that's kind of the general form of stress. We can divide by A, and we can say that strain is now equal to stress over A. And so by doing that, we can ultimately kind of cancel this EA, and we can look and now see the total strain in the Z direction is just the strain of the reference axis minus the curvature times the position in the X within the cross section, X, minus the curvature times the position in the Y, position Y within the cross section. And so, in the end, we can compute strain at all points everywhere in the beam. We also can compute the axial stretch of the reference axis as the total P divided by EA. And so, lo and behold, we can compute that to be 1 over 540,000. The units on this, of course, are change in length over length. So strain is a unitless quantity, change in length over length. Okay, so we have the overall strain. We have everything we need, really, for the overall strain. We have also, recognizing we have a symmetric cross-section, that makes these equations simplify greatly. We ultimately can calculate Ixx and Iyy. Those are the integral of x squared dA and the integral of y squared dA. And again, these second derivatives are the curvatures. Okay, knowing the moments, we've solved for the moments. Knowing the cross-section properties, which we can compute rather easily, we can solve ultimately for the curvatures. Okay, E was 30 times 10 to the 6th, so this one is E. I, this is just width BH cubed over 12, base times height cubed over 12 for a rectangular cross section. Boom, I put those numbers in here. Our moment we've already calculated as being 1500. Hence, we can calculate curvature. Boom, there it is. We can also calculate curvature of the y displacement field. That's the x moment over IXX. This one was a function of z. And so ultimately now the curvature is going to be a function of z for the curvature about the, really this is from deflection in the y-axis. Okay, so ultimately, can we compute stress? Well, we have the neutral axis strain, we have the curvatures, and we can calculate positions within a cross section, and lo and behold, we have everything we need. So I will compute stress really at two different points. At 1.5 plus 3 and 1.5 minus 3, we can compute different stresses based on that formula, and here's the answer. So that's kind of the bottom line. We have a general formula that gives it as a function of position, and then we can evaluate the stress at various positions within the beam, and lo and behold, it gives us an answer. So the takeaway from this example is, well, there's a few. One is just a review of the equations, the relationships between the moments, the curvatures, the stresses, the strains. And number two is this idea that moment can be expressed as a vector and has components that ultimately factor into these beam bending equations. Okay, do we have any questions at this point? I guess I should throw up the last slide. For the last couple of slides for this example. We can, of course, compute displacements or deflections, depending on whether you're talking about the reference line deflection or the overall displacement. To get that, of course, we just simply recognize that the strain in the z direction is the first derivative of displacement. Strain being a constant, we can calculate displacement by integrating, and that integration is straightforward. We can apply the boundary conditions on that displacement calculation, lo and behold, this becomes pretty simplistic. I don't need to go through every last detail here, but you can calculate, we know the boundary condition, the displacement at the root is going to be equal to 0. We can calculate slope at the root as being equal to 0 because this is, again, a cantilever beam. We can calculate the second order derivatives. All right, so Ron asks a question. The stress, I express stress equations as a function of z. Yes, and that is at a position x, y in the cross section. Yeah. So again, if we looked at the cross section, it looked like so. So if we had x and y, we computed really at 2 points. We computed one up here and we computed one down here. I see Amir asked a question. So Amir asked, what would be the difference between MZ and a torque? Sorry if I make you sound repetitive. Oh, that's a great question, Amir. Thanks for asking. No, it's not repetitive at all. So going back to sort of the initial discussion, this is the z-axis, and now we've computed a moment about that axis. And that is, in fact, very much a torque. very much a torque. And I kind of glossed, I guess not intentionally so, but glossed over that point. So this is torsion of a beam. So that one component, whereas mx and my contribute bending deflections and bending stresses to the beam, that component of torque contributes a torsion to the beam. And that, in fact, we haven't gotten to in our calculations yet. That's something that's going to come up in, say 3 or 4 more lectures. And it turns out it doesn't impact the stresses that we have computed, but it does impact the local shear stress at any given point within the cross section. So it doesn't change the overall resultant shear stress, that is the integration over the entirety of the area, but it does impact locally at one given point what the stress tensor, well, I should say really what the traction vector at that point is. So Amir, thanks for pointing that out. That we have not addressed that issue yet, other than to say it is a torque. So great question. Sarah asked, can you go back to the slide where you go from U comma ZZ, V comma ZZ to sigma ZZ? Yeah, so that's this equation here. Did you have a more specific question about that? So this equation was one of the equations that we derived last lecture. And you know, it came, where did it come from? It came from the assumed displacement field of the reference line. I should say the assumed displacement field of the entire beam, which is assumed to be directly attributable to the reference line deflections. Remember, that was the idea of plane sections remain plane and they remain perpendicular to the reference line. And when that occurs, then we can say that the deflection is a linear function of position within the cross section with respect to the reference axis, and overall then strain becomes a second order term because it's the derivative of that position. Did that address your overall question, Sarah? I'm not sure entirely what was unclear about that, but I'm happy to address the question if I haven't yet. Okay, I'm not hearing from Sarah. Still a little confused about how you got to the n sigma values. Yeah, so basically what I did is I just plugged this value in there. I plugged this value in there. And I plugged this value, which is a function of z, in there. And now after plugging that in, sigma zz, well, it's going to be a function of, what's it going to be a function of? It's going to be a function of x, because that's still an unknown. So that's this x here, x. Here's a y. And then last but not least, since we plugged in z, it is going to be a function of z. And if I failed to make it clear exactly what I was doing, it's probably because I dropped the z in writing these equations. So really this is x and y positions, and I should have had a z in there, and implicitly in these two we have z equal to 0. Does that help, Sarah? Okay, great. All right. let's see here. It is now, what time is it? 3:30. So we have about 20 minutes left. I think we've gotten now to the end of this lecture. So that was really the conclusion of the last lecture. So the next thing we're going to do is move forward. Start the next lecture. This is really formally lecture 13, the beginning, in the way, at least in the numbering scheme we're using. The topic now is beam shear. Really what we're now going to express is solutions for a somewhat different problem. It's in fact a very similar problem, but now we're going to put an additional geometric constraint on the problem. Now previously we defined an Euler-Bernoulli beam. What did we say? Well, just or a beam in general, we'll start with just the beam in general. A beam in general has one geometric feature, its length, that is much greater than the in-plane cross-sectional dimensions. So really, it's longer in one dimension than the other two. We also said that when it deforms, assuming that the beam is long, we observed that plane sections remain plane and they remain perpendicular to the neutral axis. That was, just to remind you, we watched that YouTube video because if we were in the real lecture hall, I would have brought my own foam beam and we would have bent it and gone through and really thought through all of those problems. In this lecture, of course, we had to do it with a YouTube video, but I think functionally it ended up being able to communicate that to you. So a beam is something that's long relative to its other two dimensions. It has a special deformation that's associated with it. And really, those were the limitations. We hadn't really said, well, what does the cross-section look like? You know, in the examples that we provided, the cross-section was pretty much a rectangular or square or circular cross-section, you know, nothing particularly special about the cross-section. Now we're going to limit ourselves to discussing a beam that is instead going to be a thin beam. So when we're talking about thin beams, as we look at it, again, so, and let me draw the beam now, again, goes off in this direction, and it's going to be long in that direction relative to its cross-sectional representative length, its characteristic length. However, we're putting a new constraint on it. That constraint is that it's going to be thin in this direction. Now that's a really interesting constraint to put on because that begins to allow us to make some additional statements about the strain and stress fields as they regard deflections that are present in these beams. So before we do that, I'm going to, for convenience, it's a very much only a convenience thing, I'm going to define a new coordinate system. So the coordinate system that we've been using aligned the z-axis with the long axis of the beam. It aligned the x and y axes with the in-plane cross-section, where the origin of the xy axes was at the centroid of the cross-section. But that turns out to be a relatively inconvenient coordinate system for the purposes of beams that are thin. So I'm going to define a new one. Here, I'll circle it for you. The new coordinate system is now a tangent normal coordinate system, where S is now something that is tangent to a line that describes the thin cross-section of the beam. So the position of the thin wall of the beam within the cross-section. I see Aiden has asked a question. Aiden says, like we defined with the beams, saying as a general rule, the length had to be about 8 times longer than the other dimension. Is there a convention for defining thin? Oh, what a wonderful question. Thanks, Aiden, for asking it. Is there a convention? This one, again, is relatively loose. Previously, I said, well, it's greater than 10 times, probably can get away with 8 times, often can get away with 5 times. What does thin mean? I would say that those numbers that we used previously, 5, 8, 10, are, again, some good guideline numbers to use. The theory that we will now develop is in fact quite accurate when the wall is thin. However, it gets worse as the wall moves away from being thin. And so again, these are all relative numbers. If later in the series of lectures, we might say define a circular cross section and then a wall thickness. And now, of course, we have a wall thickness, which is thin relative to the overall radius. And so if we said that T over R, where R is the radius, T is the thickness, I would say has to be, again, this is greater than or equal to about, I like that number 8 for some reason. It's a good number to use. Could accept 5 in some circumstances. Sometimes you want to go higher. So wonderful question. Anyway, so here we have to make some assumptions now. So again, we've defined a new coordinate system. I've chosen in this particular drawing to orient that coordinate system at a free edge for reasons that will become obvious as we move forward. Although in general, it doesn't have to be defined at a free edge, and there are many circumstances where it won't be. Excuse me. We're going to assume the wall is thin. I'm redundant when I state that. But when I state it now, I'm going to put some mathematics to it. What I'm going to say is that the thickness of the wall is now a function of position within the cross-section. And that function now is defined by the coordinate system S. Here's the last one, and this is perhaps the most important, and one that I feel like I might have to convince you a little bit about. That is that the shear stress does not vary through the thickness. Okay, what do I mean? So if I were to draw, let me go back to this drawing that I put up here now. Erase some of the unnecessary stuff. One of the things that you'll find is oops, push the wrong button, so I'm going to erase just a little more. Here at this point, there is shear. Okay, that shear stress that's occurring, we have repeatedly referenced these loads that beams carry. That is the axial force P, the shear force S, the moment M. Those all were resultants. That means that it's the integral over the entirety of the area of the cross-section. In order to have S be non-zero, the shear resultant be non-zero, we have to have shear present on the cross-section. So this is what I'm really talking about now, is the shear stress that's present at a position S. So S now defines our location within the cross-section, and Z defines our location along the length of the beam. So at any point in this section, what I'm saying is that the shear stress does not vary through the thickness. Now, I think to convince you of that might take a little bit of work. Let me make an attempt. How come I'm not getting my chalkboard? Anyway, now, how do we make this argument? Okay, ultimately, it comes from a couple of things. I'm going to draw just a thin section here. I'm going to draw it horizontal for now. On the top and bottom surface of this thin section, you could conceivably have normal stress. However, the way these are drawn, and with the loads being resultants, these beams typically have no lateral loads that would be applicable. So we have essentially that, in the way I'm drawing it here, sigma yy is equal to 0 on the top surface. Sigma yy is equal to 0 on the bottom surface. And so we really have no large magnitude, certainly sigma yy, anywhere through the thickness, because on the top surface it's small, on the bottom surface it's small, and there's no geometric space for there to build up any stress. Okay, the other thing to keep in mind is the equations, the governing differential equations for stress. Let me see if I can write them for you here. In fact, here I got my chalkboard back. So if you remember, I had sigma xx comma x plus sigma xy comma y plus sigma xz comma z was equal to 0. We're going to drop the acceleration terms on the right-hand side. Similarly, we had sigma xy comma x plus sigma yy comma y plus sigma yz comma z is equal to 0. Now we're going to, just for the sake of argument, with the way I've drawn my figure here, I'm going to say that, boom, the z terms go to 0 just because we have no z stress present in this horizontal section that I've drawn. And then you can look at this term here. I'll highlight, this is the equation really of interest. Why? Well, because what do we see? We see that sigma yy comma y is present in this equation. This is the change in the y stress as a function of the y position. Well, if sigma yy is 0 in all cases, then this has to be equal to 0. Therefore, this one has to be equal to 0. And lo and behold, then when you plug in all these equations, what we find is that the through thickness, there can be no change in the shear stress through the thickness. Okay, because sigma yy is 0, because the gradients are governed by that governing differential equation, the one I just was writing, we can make this statement that through thickness the stress does not change. Okay, now moving forward from that point, we can remember, of course, also that the shear force and moment resultants, these were derived previously. dmy dz is equal to minus sx, dmx dz is equal to sy positive. Let me make another statement. Now, this one's a big one. And by the way, today's lecture is one of the unique lectures, I think, that is not nearly as useful when you are doing it online as it would be if we were in person. Okay, and I apologize about that, but that is the state of the world we're living in. For this, this next slide, I want you guys all to do this little exercise for me. Take out a piece of paper, plain sheet of paper. Well, it's really not a good demonstration to do. You know what? It is, let's see here. We have 5 minutes left, 4 minutes left, really. 15:46 is what I'm seeing on my clock, 3:46. I have 4 minutes. Why don't we stop here? And I will come back on Thursday with this lecture. I'm going to find either a video that I can show you, or I'll make one myself to help you think through this next few comments that I think are not nearly as well describable in a online lecture format as if it were in person or maybe by video. So I'm going to stop here and come back. Any questions before we move on? I mean, before we quit for the day?